Hello, I welcome you to another part of the internal forces course. Today, we will calculate the internal forces in a truss. I will show you what the Ritter method is, or the method of sections. We have such an example. For the given truss, identify the zero force members and determine the forces in all the members using the Ritter method. The Ritter method involves cutting the truss into two parts, showing the forces in the members through which we cut, and writing the static equilibrium equations for the severed part. We have three equilibrium equations, so we can calculate three unknowns. We will have something called Ritter points, which are the points where the directions of the members we cut through intersect. We will make moment sums at these Ritter points. We have this truss. I have numbered the members from 1 to 13 and marked the support reactions. So we calculate the support reactions. I won't dwell on this. You can refer to previous videos. If you still have problems with this, we will first calculate the sum of moments at point A to determine the reaction VB. From this, the reaction VB is minus 24.375. This means I assumed the direction wrong. I am changing it to positive here, and I changed the direction of reaction VB to the opposite. So let's continue. The sum of projections on the y-axis equals 0. From this we get that VA upwards, plus 15, minus VB, and here plus another 15 should equal 0. From this, the reaction VA again turns out negative. That means I assumed this direction wrong as well, so we change it to the opposite, and here we add a plus. And we are left with the sum of projections of forces on the x-axis. So we have HA plus 20 plus 10 equals 0, from which HA equals minus 30. So I assumed all reactions incorrectly, but that's okay. Plus, and we know everything. Let's do a check. If you are doing a check, do it at a point through which no reaction passes. I did it where members 1, 2, and 6 converge, so 1, 2, and 6 meet here. At this point, we will do the sum of moments as a check. So we have HA acting to the left, which means it rotates positively around this point. So positive HA times 3, minus VA times 4, plus VB times 4, minus 15 times 7, and minus 20 times 3 equals 0. So indeed it checks out. 0 equals 0, left equals right. Now we move on to the Ritter method. So we need to cut through 3 members, or 2. So we could cut, for example, here if we wanted to, through 2. And for 3 we can cut like this, or here, or here. I don't think there are more options. I will first show you the cut through the middle of the truss. Because, for example, many problems with the Ritter method involve calculating reactions in the members, and usually the middle members are given. Because the Ritter method is most useful when we need to calculate forces in specific members, and most often if they are located in the center, if we were to approach it through the equilibrium of nodes, well, so here we need to balance the first node, then we have to balance this one, then we have to balance this one. Only then will we have that force. So we make one cut. We have 3 unknowns and 3 equations, the sum of moments for 3 Ritter points, and then we can directly calculate the 3 bars we are interested in, the forces in them. All right, as I said, first we will make a cut through bars 2, 7, 12, and calculate the reactions in the bars, specifically in the 2nd, 7th, and 12th. This is what our cut looks like. And we can arbitrarily disregard one side. We can disregard everything on the left side or everything on the right side. So we deal with either the cut on the left or on the right side. We disregard the side where we have more forces. Well, we have more forces on the right side, so we disregard that right side. And at the points of intersection, we show the forces that are in these bars. That is the force in bar 2, the force in bar 7, and the force in bar 12. I assume from the cross-section to the outside, which means I assume that the bars are being stretched. If the calculations yield a positive result, It means they are indeed stretched, and if it yields a negative result, it means I assumed the wrong direction and the bar is being compressed. And we have something like this. I drew those reactions and here I extended the dashed line because this is one of the Ritter points. Here, the forces N2 and N7 converge at this point. At this point, the forces N7 and N12 converge, these two unknowns. So when we sum the moments at this point, I might label them point 1, point 2, and point 3 here, so we will also do it in such an order. When we sum the moments at point 1, then N2 and N7 pass through, we directly calculate N12. Then we will do it at point 2, where N7 and N12 pass through this point, so they do not create a moment. We directly calculate N2, and then for any point we actually calculate the sum of moments. It could be at this third point, and we calculate the remaining reaction that we have not calculated so far, which is N7. So let's get to work. The sum of moments at point 1 equals 0. Minus N12 because it is counterclockwise on arm 3. Of course, when forces are applied to the truss, we redraw them all. So here is the force, so we account for it here. If we had a cut on the right side, then all those forces would also have to be considered. So we have plus this 15 on arm 4, plus reaction 30 on arm 3, and minus reaction 5.625 on arm 8. This should equal 0. From this, we calculate the reaction N12 equal to 35 kN. Now the sum of moments at point 2. It should equal 0. So we have this N2 on arm 3 minus 5.625 on arm 4. 30 goes through point 2, 15 goes through point 2, N7 and N12 too. From this, the reaction N2 equals 7.5 kN, and we are left to calculate only the reaction N7. Well, now we need to resolve it. We don't have to, but it's most convenient to break it down into component X and component Y. Or alternatively, we can calculate the arm of the action for this reaction N7. Relative to point 3, the arm of the action is the perpendicular distance from the direction of action to the point for which we are calculating the moment. So we would need to draw a perpendicular line here and determine its length. Then we wouldn't need to break this force into components, but I still recommend breaking it down. So now we will break down N7. And now there's this issue. The reaction N7 is along the entire length of the rod. If someone breaks down N7 as I drew, let's say in the way I did, all right, we are breaking down N7. So here is the vertical component and the horizontal component. And then we would start to wonder at what arm the vertical component acts relative to point 3. And at what arm, in that case, does the horizontal component act relative to point 3? Well, you can get tripped up here too, but you have to be careful, as I mentioned. This reaction N7 is along the entire length of the rod. We can move to the second node here and draw the components. So the vertical component will be N7Y. I will write just Y because N7 won't come out for me here. And the horizontal component, I will write X here. All right, 7X, I don't know, to avoid confusion, and 7Y. So this is the reaction N7Y, the vertical component, and N7X, the horizontal component, from this force in the rod N7. So now, as you know, we need to determine some angle, meaning the sine and cosine of a certain angle with respect to this slanted rod. All right, I will assume that there is some angle alpha here. So in that case, the sine of this angle is 4 to the hypotenuse. So we have a triangle 3, 4, 5 that is 4 to 5, 0.8. And the cosine of this angle is 3 to 5, which is 0.6. And you remember from previous videos that if we have here a reaction, some force N7, the component that has the angle, that is the vertical one, is with the cosine of that angle, while the other component is with the sine of that angle. So I remind you, we are calculating the moment at point 3. So notice that the component N7Y passes through this moment pole. N7Y passes through the moment pole, but the horizontal component does not pass. So only the horizontal component creates a moment. So it is with the sine, right? So it is in this position. It turns counterclockwise, that is in 7 times sine alpha, that is this component. And it acts on an arm of 3 meters, and turns counterclockwise, which is negative. So we have minus n7 times sine alpha times the arm 3 meters. The vertical component passes through the pole and does not create a moment. Here earlier I noted negative n12, which acts on the same arm of 3 meters, plus that 30 on the arm of 3 meters, and minus the reaction 5.625 on the arm of 4 meters. It must equal 0. For sine alpha, of course, we substitute 0.8, and from this we calculate the reaction n7, remembering that n12 is 35 kN, and thus n7 results in minus 15.625 kN. Okay, let's move to the next slide and do further cuts. Now let's make a cut through these bars 1, 5, and 11. We will calculate the reactions N1, N5, and N11. This is what the cut looks like, but one more thing. We have not yet defined the 0 bars, so let's talk about this now. We will talk about the 0 bars. I talked more about 0 bars in the previous video on the method of equilibrium of nodes, so here I won't dwell on it too much. So just notice. We look at suspicious nodes like this. Here we have 3 bars where one is angled, so none of the statements about 0 bars apply here. And here we have 15 upwards. So if we were to cut this node from the sum of projections on the y-axis, this bar 6 must only take that 15. Only and exclusively. But we will discuss this when calculating the reactions. But let's look at this node. Bars 3 and 10 converge here, and we have a force of 10 pushing to the right. So if we were to cut this node and do the sum of projections on the y-axis, N3 only enters the sum of projections on the x-axis. The force of 10 does too, and it would come out that N10 equals 0. So this is a 0 bar. Well, good. Here there are no more 0 bars. Here in this node, one can nicely transfer that reaction to bar 8. And now N11, notice, must equal 30 kN. Because if here we cut this node from the sum of forces projections on the x-axis, the force in the 11th bar directly takes the horizontal reaction. Bar 11 is being stretched. It's good to notice such things. So if we cut this node, we can see that bar 4 must take the vertical reaction, which is here bar 4 is being stretched. And bar 11 must take only the 30 kN reaction. I encourage you to watch the Truss course using the method of equilibrium of nodes. So we know from here that the force in bar 11 will act this way, and that will be 30, because it takes that 30 reaction. So here we already know that N11 will be 30. So here we will have one less equation. Ritter points, so here we will only need 0.4. Well, not just 0.4. We will also do one more equation later because we need to make 2 equations. We have 2 unknowns, meaning N11 is calculated, we want N1 and N5. When we calculate the moment sum at 0.4, we will determine N1. So the sum of moments at 0.4 equals 0. The reaction of 5.625 at arm 4, counterclockwise, that is negative, plus N1 at arm 3 equals 0. From this, N1 equals 7.5 kN. Now we will do it at point A. Well, point A, because here were the reactions VA and HA. So here, well, N1 is included in this equation and N5. So we need to break N5 down into components again. That is, I again reduce it to this node and break it into components here. This will be the vertical component. This will be the horizontal component. So this will be N5x and this will be N5y. We had an angle there where the sine was 0.8. So where is now that angle whose sine is 0.8? Well, here. So we will have 4 to 5, which is 0.8. Therefore, when we do the moment for this point, the y component passes through the moment pole. The vertical reaction passes here, 30 passes, N11 passes. The only two forces are N5x, the horizontal component turns clockwise, and N1 clockwise. So I wrote the sine cosine because we have the same angle indicated. And N1 at arm 3, positively clockwise, plus N5 times sine alpha because here is N5. So projected onto the x-axis, that is not where we marked the angle with sine, but where the angle would be with cosine. So this is the force, N5 times sine alpha at arm 3 meters, should equal 0. From this we calculate the reaction N1, so we calculate the reaction N5. And it turns out to be minus 9.375 kN. We still have the intersections through rods 3, 9, and 13, so now we will calculate the forces in rods 3, 9, and 13. And again, what I mentioned a moment ago, if we look at this node, we see right away that this is 0, first of all. And secondly, rod 3 must balance this horizontal force of 10 kN, meaning the internal forces are directed inward. If the rod is being stretched, then the force in the rod is directed from the node outward, toward the center of the rod. So we mark point 5 and point 6. At these points we will perform the moment, as here we have two unknown forces converging. From this we will calculate N13, and then we remember that we have N3 calculated, so we don't need to sum the moments here. Because in this equation, if we did this, there would be an unknown N3, but we already know its value. So we will do it at any other point. It could be at point 6, and with N13 already calculated, we will calculate the reaction N9. We also remember that the last part of the truss has different dimensions than the other two, because here it was 4 by 3, and now we have 3 by 3, which means we have a different angle, simply 45 degrees. So the sine equals the cosine, which equals the square root of 2 over 2. So the sum of moments at point 5 equals 0. From this we will calculate the reaction N13. So we have the equation like this, N13 clockwise, meaning positive on arm 3, minus 15 on arm 3, and minus 20 on arm 3, equals 0. The 10 passes through these points, so it doesn't create a moment. From this, N13 is equal to 35 kN. And the sum of moments at point 6 equals 0. I won't break down the angles here anymore, because I just explained how it will look, so we will make the sum here. So N3 goes through, the 10 goes through, and 15 goes through that vertical one. In that case, we have N13 on arm 3 minus 20 on arm 3. And now the x and y components equal N9 square roots of 2 over 2. And here only the horizontal creates a moment, and I will mark it. These are the force components of N9. We see that the vertical component passes through point 6, so it doesn't create a moment. And the horizontal component equals N9 square roots of 2 over 2. On arm 3 creates a positive moment. This equals 0. From this we calculate N9, which is minus 15 square roots of 2, or minus 21.21 kN. Now, for the remaining bars that we haven't calculated yet, well, notice we have calculated bars 1, 5, 11, 2, 7, 12, 3, 9, 13. That is, all the vertical ones. I will cross them out. We have them calculated. We noted down here 0. So now we look at this joint. It is immediately evident that from the equilibrium of the joint, bar 8 must take that vertical reaction. That is, the force here must be directed oppositely to that reaction to balance it. So here we know what we have, and that will also be a positive reaction. And now the force in bar 4. Here, from the sum of projections onto the x-axis, this horizontal bar received that 30. And this vertical bar must take that reaction 5.625, which is a force directed oppositely to the reaction. Here we also have from the other side of the bar a force inward, plus bar 6, a simple situation. Bar 6 must only balance that force of 15 kN. If we cut this joint, the bar is being stretched. The force in this bar 6, done. We have everything. Everything is done. And now I remind you of the convention for labeling. We are rewriting these reactions from the previous slide, N12, N2, and N7, and I remind you that if the rod is being stretched, the direction of the internal force in the rod is towards the inside of the rod. And if the rod is being compressed, the directions are towards the outside of the rod. So the graph looks like this, and all right, let's go through all the rods from the left. We look at this rod, we have 5.625, as I said here, vertical rod 7.5. This is the first rod. We calculated the reactions here, where we had calculated positive 7.5 comma, which means towards the inside. The fifth rod, here we calculated negative 9.375 comma, which means towards the outside, this horizontal rod. Here 30 transfers what we talked about. Here vertical rod, and I marked 0 here. I marked it incorrectly. Here we have, as I said, the rod takes a force of 15 kN. So it looks like this, no 0 here vertical rod, so N2, which was calculated on the first slide, 7.5 kN positive, meaning towards the inside. This rod N7, calculated on the previous slide, minus 15 towards the outside. Rod 12, positive force 35 kN towards the inside. We have written down this vertical rod. At the top a 10, as I told you, the reaction N9 calculated here, minus 21.21 towards the outside. And the reaction here in 13, which was calculated here. Here in 13 equal sign, 35 kN positive, so towards the inside. Everything adds up. Here we have 1,0 rod. And this is how the Ritter method looks. It is primarily helpful in calculations, when we need to calculate some rods in the middle of a truss. If the truss is quite troublesome, has a chord at an angle, I'll show you such a truss in a moment. There are a lot of angles to be determined, and balancing these nodes one by one is tedious and laborious. That's when the Ritter method comes in handy if we really need to determine those forces in the rods somewhere in the middle of the truss. Well, I hope I haven't forgotten anything. I've said everything I wanted to say. So I have a second example for you, which you can solve. For this truss, we need to calculate the reactions in the indicated rods, N1, N2, and 3. I marked rod 1, rod 2, and rod 3 here. And if you feel like it, do this, using the Ritter method, cut through these 3 rods. Of course, at the beginning you need to calculate the reactions. And I encourage you to write your proposed answers in the comments under the video. I will reply to you whether you calculated correctly or not. And that's all for today. Thanks for your attention. If anything was unclear in this video, feel free to ask questions under the video as well. I encourage you to like our Facebook profile. Take care, bye!